Hello everyone, and welcome to this video. Here I will try to explain to you what a sparse Čech filtration is and also give some geometric intuition for how it works. And I would say we jump right in to the setting. So let P be a finite point cloud in R to the D, and let PT be the union of balls or the Čech filtration on P, so a very standard setting. And the classical TDA pipeline would now be to first compute the nerve of this filtration. So we get a filtered simplicial complex, which we then can compute the persistence diagram of to get the topological properties of a point cloud P. And very standard problem that arises with this approach is that if the point cloud P has size n, then its k-skeleton of the nerve will have size O of n to the k. And if n is the size of a reasonable real-world data set, n to the k will be way too large for practical computations. So the idea of sparse filtrations is to approximate the Čech filtration, which is a much smaller one. And the idea here is to delete irrelevant balls. More precisely, the geometric idea of the filtration that I will present today is that balls that are close together almost contain each other in later stages. One example for this is this point cloud. Here we have only 4 points, but 2 of them are very close together. And if we now get the normal Čech filtration going, we see that after a while, for example here, that the points that are too close together have their balls overlapping by a very large amount. And we could now say that if we just want an approximation of a filtration, we could just delete the ball around x3 and just keep the ball around x2 because they cover very similar areas of RD. And the way we can do this is to just stop the ball around x3 from growing for a small amount of time, which I will color in red. And after it's been completely swallowed, we can then just delete the ball around x3 because the area covered by the ball around x3 is also covered by the ball around x2. And this I will mark with gray. So yeah, that's basically the idea. And the formal statement of this approximation is the following. So let epsilon be approximation parameter between 0 and 1. And the approximation will get more sharp for small epsilon. Yeah, then there is an approximation p tilde t of pt such that the following holds. Pt and p tilde t are epsilon interleaved. And note that this is not a classical interleaving, this is a multiplicative interleaving, which basically means that the approximation of a filtration pt gets worse for large t, but better for small t, because we don't add a factor of plus epsilon in the index, but we multiply by 1 plus epsilon. Secondly, the k-skeleton of the nerve of p tilde t can be computed in n times some constant time. The constant is looking quite large, but in theory, this is still linear time. So it's a very big improvement to n to the k for general k. And also this follows from the second point, the skeleton only contains linearly many simplices. So we have a linear sized approximation of a otherwise very large complex. There's a few technical remarks about the constant and the filtration, and you can pause the video for a second if you want to take a look. So now to the construction of p tilde t. Given our geometric idea, we basically have to do 2 things. We have to, for every p in our point cloud, specify a shrink time, which is some number in 0 infinity, and a death time, which is greater than the shrink time, such that the ball around the point stops growing at S, and we can delete this ball at D. And these have to satisfy 2 things, such that we actually get a good approximation. First, for the 1 plus epsilon interleaving, we need to make sure we don't shrink the ball around P for a too long amount of time. So not by more than a factor of 1 plus epsilon, which basically means that D should be less than or equal to 1 plus epsilon times S. And this is just because we want to get a 1 plus epsilon interleaving. Secondly, the ball of radius S around P should be covered by another ball before it dies at D. Otherwise, we don't get inclusion of sets, in RD, and we don't get a topological filtration of spaces, and the whole framework of topological data analysis breaks down. So these two are really important. And the way we get our approximation is by first finding a greedy permutation of the point cloud. And we find this one as follows. So at first, we only choose a single point, which can be viewed as like the first very rough approximation of the point cloud. And then to get better approximations, we continue inductively by always choosing next the point which is farthest away from all the other points we've chosen. So in this case, the second point in the permutation would just be the one at the bottom right, P2, and it would have distance lambda 2 from all the other points we've chosen so far, which is just P1. Then we continue and choose the next point, P3, which is distance lambda 3 from P2, and so on. The nice thing about doing it in this way is that we actually get a really good covering of a point cloud at every stage, meaning that if we look at this distance lambda 3 and the first 2 points we've chosen, actually every point in this point cloud is contained in the 2 balls around P1 and P2 of radius lambda 3. And this, of course, works at every stage k, that every point is contained in the balls of radius lambda k plus 1 around the points P1 to Pk. And yeah, to continue computing a greedy permutation, we just do this again and again and again until we've exhausted the whole point cloud. Again, the properties of a greedy permutation, Pj lambda j, are the following, and I will also write big Pj for the first j points. First, we have monotonicity. So infinity will be the distance from the first point to the empty set, just by convention. And then all the other insertion radii will be smaller and smaller until lambda n is just the distance from the last inserted point to any other point in the point cloud. Secondly, we have the covering property. So any p and p will have distance to pj less than or equal to lambda j plus 1, because we always choose lambda j plus 1 to be the distance to the farthest away point. So any other point will be even closer. And this covering property is really key to getting the approximation going. With this out of the way, we can now actually define or shrink in death times. So we will choose Sj to be 1 plus epsilon over epsilon lambda j and dj to be 1 plus epsilon times Sj. And don't worry about the precise values of these numbers too much. They essentially pop out of the computation in the end. And the balls using these values are defined as expected. So for t less than the shrink time, the ball is just the usual ball of radius t around pj. Then we stop the modified ball bj from growing until the death time, and then we can delete it for larger t. So the modified balls will be denoted as bj. And some notes about this definition. You can note that for small j, the ball bj, so the modified ball, will live longer, which essentially means that points we choose earlier in the greedy permutation are more important for the topology of the point cloud. And for smaller epsilon, all Sj will be larger, so we essentially get a tighter approximation because we shrink the balls less or later. And now we still have to check, why does this precise definition actually work? And why do we get a good approximation and a filtration in the end? For the question of why do we get a filtration, we have to prove some lemma like the following one. So let pj be any point in P. And if t is now larger than the death time, we should want some ball with index I, such that the final sized ball around pj is included in this ball. So we don't ever delete anything from the set which was not already contained in another ball. And you could think, as like your first idea of proving this, that we should choose I just to be the index of the closest point to pj, because the ball around pi should be the closest to the ball around pj, and so we should have the best chances of covering it. The problem is we need to have some control about the death time about that ball too, because it could happen that the ball around pi also just dies before we reach t, and then both balls need to be covered by another ball. and we didn't get anywhere. So we need to continue a bit more cleverly and use the greedy permutation better. So the new attempt is to find the shrink time sk such that k is as large as possible and sk is greater than or equal to t. So in formulas, it is sk plus 1 is less than or equal to t is less than or equal to sk. And this essentially just means that all pi in the set pk have shrink times greater than t, and as such very good candidates of covering our ball around pj, because they don't stop shrinking until the time step t is reached. And now we just choose pi not the closest point to bj, but just the closest point in the set of points that just don't die too early. And geometrically, this looks like the following. We have some point cloud P and the chosen point Pj we want to cover. And we have our point set Pk of points with death times that are not too large. And now we choose the closest point Pi to Pj in this Pk. And now we want to see that any point in the ball Sj around Pj is only at most t away from pi, such that it is covered in early enough to not ruin the filtration. And with the definitions we've given so far, this is actually just applications of the definitions and the triangle inequality. And I will just skip quickly over the computations here. And in the end, we can conclude that we actually do get the covering and the filtration, which is really cool. And now we just have to see that this p tilde t is a good approximation, which is actually quite easy to see by construction, because we only have to show the interleaving. And one step of the interleaving is really easy, because our approximation, just as sets in RD, is always a bit smaller than the usual Čech filtration, because we only shrink or delete balls. We never add anything to the set. So this inclusion is quite free. And the other inclusion, formally you would show it with like another triangle inequality argument, but we can see it a bit more informally by noting that our construction of the modified balls bj of t only modifies the balls in a time scale of sj to 1 plus epsilon times sj. So essentially, if we give the approximation filtration a head start of 1 plus epsilon, the usual Čech filtration should always keep up. And in conclusion, we see that the set pk approximates p well on different timescales, and in this case, it's timescales sk plus 1 to sk. And if we choose the right set on the right timescale, we always obtain some approximation of our filtration with just very few points. And that's it for the construction and the geometric intuition. What's still missing to make this into a good theory is, of course, the computational aspect. So we need to see that the K-skeleton of the nerve is actually of linear size. And we have to see that we can compute this nerve efficiently, meaning in also somewhat linear time. And this is done in my source material, a geometric perspective on sparse filtrations by Kavanas, Jahansi, and Sheehy, which can be found online, and I will also put it in the video description. And also, as one last remark, note that this theory is actually a quite theoretical result. You can implement it, but in practice, some modified methods with worse theoretical results will perform better. And they often use similar ideas though. So I hope you'll still find the ideas in this video somewhat helpful if you encounter one of these sparse filtration at some point. And as a very last thing, I'll show you a short demonstration of this filtration actually going on. So here we have some point cloud in R2. And yeah, I'll just get the filtration going. And we see that after a short amount of time, not actually that many balls have been removed. So we have these 2 balls being removed already, which are grayed out, where 2 points are actually very close to each other and don't contribute much to the topology at all. And some balls have already stopped growing, the ones marked in red. But if we now continue we see that actually as it gets really cluttered and many areas of the point cloud get multi-covered, a lot of points get deleted. So this seems to be one of the strengths in this filtration, that these areas which have a lot of redundant covering get rid of a lot of the points and balls in our point cloud. And yeah, that's it from me. I hope you took something away from this, and I hope you have a nice day.